So I want to talk about decision making because that's what we're all here for. I want to make the point that statistical methods interpret the past, but decisions are based on incomplete knowledge. But decision making is about the future. And I'm an engineer, so I want to know, well, what are the fundamental limitations that we have to deal with? And predicting the future is not easy. Some of you may have lived through this hurricane, but you can see, you know exactly where you are here, but a few days later, this thing could be anywhere. And this is the best prediction that money can buy. So it tells you how good predicting the future is. So what's the problem with the future? Well, complexity. The world is complex, but it's not random. It requires an immense number of variables to describe a model. Many variables are not known or measured. Many causal relationships are hidden. Predictive models, as I think someone said last night, predictive models are not predictive outside of the range of the training data set. And if there is good news, it is big data done using computers. Here's another problem with the future, and that is chaotic processes. I'm sure you're familiar that some environmental situations are chaotic, like the population of certain types of animals, the rabbits and the foxes and that sort of thing. But this is the Lorenz attractor, one of the first ones. Chaotic systems are extremely sensitive to initial conditions. They do not have equilibrium states. There is limited predictability. I mean, if you know you're here, then you can predict a little ways into the future. But it's just like this weather thing. The further out you try to go, the less certainty you have. So this is a severe limitation. But there is good news, and that is you have to look at chaotic systems from a different point of view, and that is, what is the dimensionality of your chaotic attractor? If you can find one, what is the dimensionality of the system? And that gives you a hint as to the complexity of the system. This Lorenz attractor here, it's got two attractors here and here. They flip back and forth from time to time. It takes about 3 dimensions to fill up. A Lorenz attractor can fill up about 3 dimensions, so that gives you a clue as to the complexity of the attractor. Nonlinearity, another problem. Engineers deal with this problem all the time. And of course, as you know, 2x fertilizer doesn't produce 2x yield. Well, complex processes are inherently nonlinear. And nonlinear relationships are difficult to deal with. And there's good news. Computational methods for nonlinear systems. I studied finite element methods. And then, of course, more good news is the ascendancy of artificial intelligence, and in particular neural networks. And they are inherently nonlinear technologies themselves, artificial neural networks. So there's hope there. Okay, here's another problem. Quantum processes. You may have seen a while back, quantum tunneling and photosynthesis increases photosynthetic efficiency. But we're still fighting at the atomic level. There's the Heisenberg uncertainty principle. Delta position times difference in momentum is equal to Planck's constant over 2 pi. That's a fundamental limitation. But at the Newtonian level, that all averages out. So the effect is very small. But here's the bad news, and that is biology works right down in that transition zone from Newtonian to quantum, or the other way, from quantum up to Newtonian. And that region is very, very difficult to describe mathematically. Another problem about the future is the likelihood of improbable events. The future, if you think of it in the abstract, there are so many possibilities, each one of which is highly improbable, but it is a statistical certainty that improbable events will occur. And here's an example. The birthday problem. In a room of 23 people, the chance of having 2 people have the same birth date is more than 50%. And in a room this size, it's greater. I don't know what it is, but if anybody wants to do it later on, we can take your birthdays and figure it out. Another problem, the high cost of knowledge. That's what I hear from everybody. People use large data sets to average out stuff that they either don't know about or can't measure. This has produced the need for more field trial instrumentation. Things like within field variations. We'll have a speaker talking about how to deal with that issue. The weather. Of course, the weather is difficult to predict, but I think one of the major seed companies has bought some weather prediction companies so they can sell crop insurance, and more power to them. Things like ratings and scores, very inexpensive, but they are imprecise and ephemeral. You look at your plant, you throw it away, you never see it again. Next year you say, oh, I wonder, what happened? What was that all about? Oh, I don't know, but it's gone now. So here's my ad. We do growth trials. They're small in size. We have a simplified growth platform. We can provide information to you which may be useful, we hope. I want to show you some examples of additional knowledge, and I think that's one of the big themes today, certainly from our Bayesian speaker, and that is how do we incorporate additional knowledge into a conclusion. I want to talk about 3 examples today that strike me as interesting. One of them is the central limit theorem. The central limit theorem basically says that if you have several different processes and they all work together, in the end you get a Gaussian. That is a proven theorem. So how does that help me? Well, if I see an experiment that has a non-Gaussian distribution, that suggests that a very few processes may be involved. And that tells me something. It tells me about the complexity of the system. So if I have a nonlinear distribution and then I can imagine how that could be the result of 2 processes, then I can look around in my experiment and I can say, well, what have I got 2 of? And maybe you've got 2 active ingredients in your stuff, so maybe that's a chance or a place to look. But it gives you another way to look at things. Something that we do here, a pattern classification. I'm sure this is done in statistics as well, but if you just look along the x-axis, you can't separate these points. If you look along the y-axis, you can't separate these data points. But if you look at the whole data set, you can see that they are separable. And this is our logo, for those of you who haven't seen it. So here's something else we did. This is additional knowledge of an entirely different sort. We were having difficulties dealing with foliar sprays that we were experimenting with for customers. And we found that the effect of a surfactant can create an incredible difference in dose rate. Here's the treatment only on a piece of maize leaf. Here it is with one surfactant, and here it is with another surfactant. You see, this surfactant gives you a much larger area, and if your active ingredient is a systemic treatment, then you will get a lot more absorption here than you will in either one of these cases here, which has a tremendous effect on the actual effective dose rate that the plant itself sees. So we put together a little machine to take this sort of picture. Those of you who have or will take the tour, I'll show you this. And of course, there are many, many other problems here, like how does the active ingredient get through the cuticle? Does it go through the stomata? We don't have the answers to all the questions, but we're working on this part of the question. That is, how does the surfactant spread out on leaves? So this, I hope, is of interest to our foliar spray guys. Again, some advertisement. How can we help you? Well, two places. One in early testing work, active ingredient concentration, the effect of adjuvants, how does it work? We have a simplified system so that we can isolate the effects of the active ingredient. I mean, if you're testing a fungicide in the field, you'll have fungus. If you test your fungicide in our lab, there won't be any fungus. So you can see, does my fungicide have a boost effect, or does it have a drag effect, or does it have no effect, or what happens? Then dose rate, how to apply it. We can do all three of these. And then over here in marketing, we can help you with things like claims justification. I mean, not to say that we can do anything deceptive, because we would not. But if you think your stuff does something, we can verify that it does so, and we can provide you with experimental documentation that says so. So that's my ad. The whole theme today is the integration of knowledge in order to better predict the future. We take a multidimensional view of all the data. We want our decisions to take into account all of the available knowledge, and that includes just your general knowledge, your past experience, and system properties. That is, I don't have to know anything about plants to know about chaotic systems or the central limit theorem. And of course, we'll have speakers on frequentist statistics and the Bayesian method. So that's my point.
Any questions?
Yes, sir.
I loved your comment on the Gaussian distribution. Can you give us a real-life example of where you've seen a non-Gaussian distribution leading to a decision that there were just a few factors involved?
I can tell you that we have seen non-Gaussian distributions, and we have pointed this out to our customer. One of the problems that we have is things like non-disclosure agreements. So we don't always know what happens, but let me give you a hypothetical. Let's suppose we've got a distribution that comes in and it's got a peak in the middle. Well, that suggests to me that this could be the result of, say, two Gaussian distributions, or two distributions of some kind that kind of overlap, and then there's that this overlapping part is where good things happen. So then you say, okay, so I've got two ingredients in my stuff, so I can look at that. And maybe there's something to do with dilution rates, or maybe the dilution rate on one is, I'd say the optimal point for one is different. So you have to change the dilution rate some way in order to get those two things to work together better. I mean, that is a hypothetical, but it illustrates the concept of how you can use this information to form a revised or better hypothesis.